Welcome to Chapter 6, and so this video starts with 6.4, which is Congruency and Similarity Revisited. So the first thing in this chapter is the Hypotenuse Let Congruency. So what that is I'm going to explain that through problem 6.17. And in 6.17, they basically give you two triangles. So that you have two triangles that are basically look fairly similar. One's like that, and one's like this. And you're given the length of two sides, and these are both right triangles, by the way. And you're given the length of two sides in each of these triangles. So you have the length of the hypotenuse of this one's 10, and this leg right here is 9. Then over here you have this is 10, and this is 9. So they ask you, are these two triangles congruent? Why or why not? So the way to find out if they're congruent is, well, these are right triangles, so let's do the Pythagorean Theorem. So 10 squared minus 9 squared is equal to this, let's call this x squared. So basically you get 10 squared, which is 100, minus 81, which is 9 squared, is equal to the square root of 19. Well, you get 19, then you square root x, so x is equal to the square root of 19, and so this is the square root of 19. Then you do the same process for this triangle and call this x, and then you get this side's also equal to the square root of 19, and so you get these two triangles are in fact congruent by side angles, side, or you could end up doing side angle side, but through side this way, you can prove that these two triangles are congruent, and that's what's called the hypotenuse let congruency, or HL congruency. And so this is one way to find out if two triangles are congruent. And so what this basically says is if there's a hypotenuse in a leg of one right triangle and it's equal to the hypotenuse in the leg of the other right triangle, then the two triangles are congruent, like the two triangles we have here. And so the next thing I'm going to talk about is hypotenuse let similarity. So the next thing in this section is hypotenuse let similarity, and that's explained in problem 6.20. So in this problem, you're given another two more triangles like the previous problem, and they're both right again. So it looks fairly similar to the previous problem, where they give you the length of two sides of the triangle, and they ask you to say whether or not these triangles are similar. So we have this side 16, this side's 20, then we have this side right here is 15, and this side's 12. And they say that this triangle is called A, B, C, and this triangle is called P, R, Q. So the way that you prove this is sort of like the last one. We need to find A, B, and RQ. And if you notice that these triangles are 3, 4, 5 triangles because they're right triangles and they follow this pattern. So you can recognize that, or you can use the Pythagorean Theorem to sort of figure out, okay, so 15 squared minus 12 squared, and that's going to end up being equal to 9 squared. So AB is equal to 9. And then you can do the same thing here where 20 squared minus 16 squared, and that's going to end up being equal to 12 squared. And so RQ is equal to 12. Now, since it's similar triangles, you look at the two triangles and then see which sides match up. So AB over RQ is equal to AC over PQ, which is equal to BC over PR. Now, you can just plug the numbers in of each side and you figure out that this is true. And so because of it, you have that triangle ABC is similar to the triangle Q are P by side, side, side similarity, since we have all three sides and they're similar because of this. And so that's hypotenuse leg similarity, because you can just do this process if you have two triangles that have the same hypotenuse and the same leg, and that proves that since this triangle has the same hypotenuse as this, or it's similar to this triangle as the leg is similar to this triangle, and it matches in here, and you could do this all. But the hypotenuse leg similarity basically just states if you have this, you can skip this step right here and just assume that these two triangles are similar if it fits the hypotenuse leg similarity. And so that's the two main points of this section. There is one more thing that I'll cover really quick. So the last point of section 6.4 is what I'm about to talk about in problem 6.18. So this problem says that they want you to prove that if the radius OC right here of circle O here, and this is the center, is perpendicular to chord AB, and so we got chord AB here of circle O, then the radius OC is bisecting chord AB. So they want to know if this is equal to this, and they want you to prove it. So it says, first of all, draw a diagram, and I've already done that here. And then it says, find a pair of congruent triangles that you can use to complete the proof. Now, what you do here is you can use what I just explained with hypotenuse leg congruency. So you can say, okay, so OA and OB are both radiuses. So OA is equal to OB. And since OX is equal to itself, you have that this is equal to itself. So you have one leg and the hypotenuse of each triangle. So since you have that the leg and the hypotenuse of this triangle is equal to the leg and hypotenuse of this triangle, you can say that triangle OAX is congruent to triangle OBX. So basically, since they are congruent, you have that AX is equal to BX. And since these two are equal, then it means that they're, this radius of OC bisects AB, and so that's how you can prove that. And so it just wants you to know that if the radius bisects a chord, then it's perpendicular